Hi everyone, this is going to be a short lecture about Clairaut's theorem. It states the following: if the D is a disk around a point A comma B in xy plane, this second derivative of xy and another second derivative of fyx are continuous, that's another condition, on that disk D. Values of these two different second order partial derivatives are equal to each other. Let's go over the meaning of this continuous function being continuous on a disk. The following is the way I introduce to avoid the approach of the point towards its AB without using the notion of continuity again. So we use this sequence of points. So it's very small here. It's x subscript n and y subscript n. So suppose a sequence is approaching this point A comma B along this path, then if the values of the function at that sequence and the other values of the partial derivative of that sequence, if they converges to the function value like this, then if we have that property, that's the definition of being continuous. So the behavior of the values of these second derivatives are kind of in our everyday notion of the continuous. There is no sudden jump or disappearance around this part here. It's all predictable, as you know, the points around this point. The values around this point, excuse me. First, we will demonstrate this geometrically, and then surprisingly this geometrically try to understand why these two values are equal to each other is very difficult. To me, it's almost impossible to see precisely why their two things are equal to each other. And after that, we will see the Taylor series approach, and from there, it's kind of blunt, straight, simple algebraic fact. So it's very interesting. Actually, this Clairaut's theorem is rooted. Its far-reaching consequences go all the way up to the differential geometry, and some of the complicated Lie bracket is really rooted to this phenomenon called this Clairaut's theorem. So it's a very interesting statement. So this will be a mathematical demonstration, and I chose this quadratic function. If you sketch the graph of this function, it's going to be a quadratic surface. So if you differentiate 2 times, and this is the only part that survives, and everything else, if you differentiate with respect to x and y, or y and x, the other 4 terms will vanish, will disappear, only this part survives. And the behavior of the first order derivative, fx and fy, becomes linear. So this demonstration is quite easy to see when you look at those numbers. If it is not quadratic, more complicated than this, it still has kind of this behavior. It's like a Taylor series. So this is going to be a good demonstration of what is it that we are observing here. So I move this slightly up so that you can see how the graph of this function look like. This is not so much of the frame, so I'm going to turn it very slowly so you can see this is the shape of the graph of this function. This is a part of the elliptic paraboloid twisted around a little bit. So this is the point we're going to look at. So let's see how this one is going to turn. This is mathematical animation I created. So this is the point, and this blue curve is where y equals 0 and x is varying, and therefore the height at z value is varying. So it's like xz curve, z as a function of x. This one is where I think x equals 0, therefore this is y z curve where y is varying and z is dependently varying. So this value here is a partial derivative with respect to x. So that will be the slope of the tangent line along this blue curve right there. So you can see that slope there, that's a negative. If you look at tangent line at that red curve, think about this tangent line right there, that will be the slope of the partial slope of that tangent line will be the partial derivative there, 0.33. So as we change this point a little bit, this will stay there, and this number and that number will change. We'll see. So I'll show you next picture and explain how we approach to the value of the second derivative fxy and fyx. So here is a slow, I don't know if you can see that or not. Now what I just did is that I took that point, look at the slope there, and I moved this point along the y-axis, and then this curve changes a little bit, and if you look at the slope here again, that's again partial derivative with respect to x. So as I go from there to there, the values of fx changes from there to there along with the y direction. So that's why this will be the good measure of fxy, first derivative with respect to x, then we move that value along with the y direction. So that value here is a 0.33, and the other value right there will be negative 4.9. Let's look at the other one. If you look at it here, the slope along that red curve will be fy, the value of fy. So if you move that base point along the x-axis, then down there will be different. If you look at the slope of the tangent line there, will be different fy value. So we move that fy along the x-axis, therefore this will be good measure of fyx. So I use the same controller, so this difference will be divided by the same number, and therefore average rate of change of fx value there and fy value there will be this one divided by the same quantity, and as you can see, these two numbers, which is the difference of these fx values and fy values, turns out exactly the same. This is in general supposed to be very close to each other, but because it's a quadratic example, it turns out it's exactly the same. And I'll show you a few other, as I change it, you can see the difference is always the same. So not only instantaneous rate right there is the same, and the average rate along all the way to any direction, I mean any amount to both directions, is always the same, but in general they're supposed to be approximately the same, and it's exactly the same in this case because we chose a quadratic example. The whole curve itself is quadratic. So this is my demonstration of Clairaut's theorem using the Mathematica animation there. Now we're back to paper, and then this is still going to be fun. Watching Mathematica thing is fun, but this will be also fun. So let's recall Taylor series. Not many of you are familiar with the Taylor series of two variable, but it's similar, so let me introduce it here. So this is how it looks like. A two variable Taylor series is supposed to be in this shape. So let's not think about the shape of the coefficient too much, so I just simply wrote all this a sub something. So the first one will be constant, and then second two terms here, and the linear term. So x minus a and y minus b, the only linear polynomial in two variables, so that fills up all the first degree. The second line is supposed to be the second degree, so here is degree 2 polynomial solely in terms of x, and here the product of x and y makes a degree 2, and product of y itself also makes a degree 2. So this is the entire collection of degree 2 polynomial. And there's degree 3 and so on. It goes to infinity. That's why I call it series. If you just freely differentiate all these terms, differentiate term by term, we get the following result if you differentiate with respect to x and then differentiate with respect to y later. Because we're differentiating two times all this degree 1 and this degree 2, because we're differentiating with respect to y, and that degree 2 term, eventually we're differentiating with respect to x, actually the first. So all of this goes away, and the only thing that survives is just 8, 1, 1. And all the other thing here has a degree 3, and we're differentiating two times, so you cannot knock down all the variable parts. So there's something always survives. So in this higher order term, there's always some x minus a or some y minus b. So if you specialize this function at a comma b, it means you plug in a and b there, This is a constant that survives. All the terms here in the parentheses has a, x minus a, or y minus b in it. So if you plug in there, it disappears, becomes 0. So that's why this value at ab is just a11. Now let's look at derivative y first and x later. It has a similar, all the things, terms here disappears, except this x minus a and y minus b survives with a constant term. Everything else, again, has this x minus a or y minus b in the term. So if we specialize the same thing, that everything disappears, the same coefficient showed up, and making these values of the two different partial derivatives equal to each other, which is known as a Clairaut's theorem. To be able to have this Taylor series, you must have a stronger condition, that's continuity, to go all the way to infinity. But this is the main class of a function when we deal with this Calc 3, so it's kind of sheds a different light on this Clairaut's theorem. But it's still it's intriguing theorem. So this is going to be not so fun part, very technical, and we go into a detail of the proof. But you know, this is always, if you think about it, this is also another fun part. You really feel the mathematics and understand the detail of the mathematics. So here's the first thing to review is a derivative. Now there are lots of variables around, so we're going to review this definition of a derivative, but you have to apply this in various different contexts. The idea is that if you're differentiating with respect to x, what's going to change is that x slot will always look like this, a plus h and a, and the other variable has to be constant. And what's different, a plus h and a has a difference h, that will go to the denominator and limit h approaches 0. This is the derivative. It's actually the idea of a derivative one variable function. So you're keeping all the other things except x parts. It's varying because we're differentiating with respect to x. And here is the same. We're differentiating with respect to y. Therefore, the first variable, x variable a, and there is fixed, and we're only playing with the y variable, like we did it for x part, and we replace it with a b plus h and b, and the difference of these two y coordinates will be h down there, so that makes the definition of a partial derivative for y. So this is going to be the beginning of the proof. I call it the setup part. It's already a bit challenging to see how this simple partial derivative applied here. So I want you to look at this part right there. Interpret this one as a partial derivative with respect to y. The function is this fx. Then we're differentiating for y. So fx is the function that fills up this function spot right there. Because we're differentiating with respect to y, this x spot a and x spot there, a is fixed. Only y, b plus h, and b is changed. So y is increased by h. It's down there. So that will be the formulation at limit. Next part really looks really ugly because we have two partial derivatives, fx and fx there. So we're going to apply this partial derivative idea both terms. So the first term here is fx. So I pull h out there first because it's a lot of denominators. So fx is a partial derivative with respect to x. So this one term here becomes two term, right? This partial derivative becomes two terms here. So this partial derivative fx becomes two terms there. Because it's x derivative, y coordinate b plus h, and b plus h, that never changes. But x coordinate is going to be something else, some different parameter, a plus l, and their l, and difference l goes to denominator. So this continues in the next line. The next term is fxab, again partial with respect to x. So b is going to be fixed. B is there, and another b is there. Good, but a part, the next derivative, is changes to a plus 8, a plus l, and a there, and difference of these two x coordinates, l go down there. So using the limit notation, we can unfold this fxy AB down to this shape. And in this part, I had this common denominator L and factored out and organized, distribute this negative here, so you see the negative and then positive there. So these are the four terms that is inside and with a limit outside there. Okay? So here I pull up these, the first bit of the proof, and so that I can show the rest of the part. Before I explain any detail, let me first explain the goal or the plan of the rest of the part of the proof. So here in this part, we looked at fxyab and kind of rewrite it as a limit form. The idea is that get rid of this limit part, just consider this quantity divided by HL here. So I wrote it like this, 1 over HL, and all these four terms appeared there. The first thing what we're going to do, using so-called the mean value theorem, we're going to turn this quantity exactly, in exact way, the value of f of fxy, the partial derivative, second order partial derivative. It's not going to be fxyab, it's something else. Then using different organization, combining different terms, we're going to change that as the value of fyx, the second order partial derivative, and some other weird points. The key thing to notice here is that this transition of this quantity written as a one form here, and that quantity written as another form here, this is done without going through any limits. This is exact equality, and that's the magic, that's the power of this use of the mean value theorem. There's often things that you can get around this mean value theorem, but I think this is really the example. This is so powerful to getting around this mean value theorem. It's so ugly and difficult, and you will really see the power of this nice mean value theorem. Now after that, once you write these two exact quantity in two different forms without using any limit, we're going to use this continuity. That was one of the hypotheses, and a continuity to AB to make that, okay, that was same quantity, and by continuity, if you use the limit, it turns out these two things must be equal to each other. So that's a rough plan. And the magic is really this use of mean value theorem, and at the end, this how this continuity of our hypothesis in the continuity hypothesis is used, and that's how it's going to go. It's very rough, and probably you did not understand everything in here that I'm trying to say, and hopefully as we go over this plan, it will make sense to you. So like I said, this is the four term divided by HL, and there's no limit to it. So I'm going to call that quantity Q. This is a quantity that depends on your tiny value of L everywhere and tiny value H everywhere, and A and B are kind of fixed. So we can say this really depends on small values of L and H, and there are independent variable H and L. So I said we're going to use mean value theorem, and let's think about mean value theorem. I'll run out of letters, so I chose this K. So K is the name of this function, one variable function, Kx. So this part is Kx plus H. That part says Kx difference, and this shows up as a part of the definition of the derivative of Kx. So if you rearrange that derivative formula, you can arrive at here. The difference of function value, usually these are applied to small value of H, and this is supposed to be the small. But if you factor out that small factor H out of that, the major constant there, constant multiple, is the values of a derivative at x star, and this x star is somewhere in between these two input value x and x plus h. There's this mysterious value not only makes these two things approximately equal, but exactly equal. There's some value that makes this one exactly equal, and that's the mean value, probably the power of the mean value theorem. So this can be viewed as a linear approximation, or if you sketch it, and then there's many different ways to understand this mean value theorem. The next part next part is it's another tricky part. When I did it myself, and if I looked at this setting, and I knew that mean value theorem is going to be useful, what I did was I looked at, okay, I'm going to look at this first two terms. Seems like b plus h and b plus h are common. So I can look at these two things as a function of x slot. So a plus l and a there, and ignore b plus h because it's not changing. And then I apply this mean value theorem. So because x parts are changing, so I enter partial derivative x, and then I choose this x star. So that was really nice. And then I tried this again to the second line. Again, it was b, and there b again is the same, and a plus l is changing. So I applied the mean value theorem again. Then there will be another mysterious choice, so that you can write this difference of this thing, these two terms, as a function of x slot there. But this x star was supposed to be different from the earlier one because it depends on b plus h, and the second line depends on b. So it's going to be different. And it was very difficult to get rid of this difference, x star there, maybe x hat there. They're different values. So here's the following trick really takes care of it, and then I hope you appreciate this really neat trick too. So rather than applying mean value theorem to this individual thing, what I just applied it here and there and there and there, it's kind of the same thing. So we're going to define it as one function. So here's how it goes. If you look at this vertical part here, b plus h and b appear there, and if you look at the second column there, b plus h and b appear the same. And if you look at the horizontal column, a plus l and a appeared. If you look at the horizontal column here, row, that's what I meant, a plus l and a there. So since a plus l and a appeared, a plus l and a appeared, they decided to call this as a function. So a plus l and a appeared. So that common part is treated as one function only. So if you look at a plus l and a part, this b plus h and b plus h the same. So we call that as a variable part, not the part that is changing. So it's tricky. But if you set it up like this x and x shows up with a common value of x star, and then difference I had before is taking care of it here. So this glx is quite tricky. Again, a plus l and a appeared there, and b plus h, so that really takes care of the horizontal line up there. So see if you get this. Now q is because the whole thing is called one function, right? And with the input b plus h, b plus h there. So it's b plus h and b plus h. So this whole thing is called now g of b plus h. And the second part is again a plus l and a plus l and a appeared, and this y slot has bb. So if I put bb, that whole thing should be called glb. So we organize this four term as a difference of two functions. And I put this L because in the definition it depends on L, but it's not, we're not going to do something about it, it's just a different notation. So that's nice. And then this is the spot where we used mean value theorem. So when we apply the mean value theorem, we apply the mean value theorem there and mean value theorem there. So that was the trick they pulled out that makes things works nicely. So this is k and k there. So this is the variable b and b. So mean value theorem says that difference of difference of this function value is the same as difference of input, which is h, times some mysterious derivative value of this function, gl prime and b star, some value in between b and bh. So that's the mean value theorem. And this h and h cancel. It's not limit, it's just a perfect cancellation, and we arrived here. 1 over L. of GL prime, the one variable derivative B star. Now this is where we go back to GL and think about differentiating with respect to x. So this part is not touched. We were differentiating this function with respect to x, differentiating with this part with respect to x. Although it's x, we're really differentiating the second slot, leaving the first part fixed. Differentiating the second slot there, leaving the first slot fixed. So this is really the partial derivative with respect to y. So that's why we have this 1 over L copied down. And this one has a two-term g of x and has two terms. But if you differentiate, this one becomes a partial derivative with respect to y, and plug in B star there. This one a is fixed, and partial derivative with respect to y there, and plug in B star. And that's the meaning of this GL prime, because this x are in y slot. Now if you look at it here, again with something that showed up, this fy, and fy is a common function, and this B star and B star is the same number, and that's the key. It's the same number that if you do this separately, you don't get the same number, and it's very difficult to treat from there. But we have the same number there. So B star and B star is fixed, only x slot is changing, therefore you can look at this as a derivative again. Derivative on x spot there, y spot's fixed. Not the derivative, I misspoke, it's mean value theorem. We're not taking any limits. Mean value theorem allows you to write this one again with the B star fixed and derivative of fy on that x slot. Therefore, there's just new value kicks in a star in between a and a plus L, and its derivative of fy will be fyx because we're doing that on the x slot. And difference between these two x input will be L. Again, these two things cancels, not because it's a limit, it's exact cancellation, and arrives at here with fyx with a star and b star, where a star and b star is number between a and a plus h, L, b and b plus h. So Q, the quantity, described as an exact way as the value of fyx. Now we're doing this again with a slightly different arrangement. So let's look at this as b plus h and b plus and b there. So we can look at b plus h. The vertical line is a b plus h and b there. And if you combine these two as a common parts, b plus h and b there. So we can look at these two things as a function, and a plus h, a plus L is the same. And for this b plus h and b, this a and a is the same. So we can look at this, the vertical line, as in that shape. B plus a showed up in the second slot, and the next slot is common, like this. So we can call that GH, and that one something GH. This H is a number, and then I used the G subscript L before, but doesn't mean that it's going to be the same if H and L is the same. It's just a notation, so it's not really indexed by quantity right there. So it's not very good notation, but I'll stick to this one. So once you write it a GH like this, and then we will arrange that for term. We'll write that for term as a two term as follows. So here, so that GH A plus L is A plus L goes there, A plus L, and A plus L goes there, and B plus H and B plus H make this one right there. So these two terms is in one notation, GH A plus L. And these two terms, B plus H and B with AA in there, will be simply this negative GHA. So that four term arranged again as a two term, but in a slightly different way than before. So here's where we use mean value theorem again. It seems like it's one variable function, and input is A plus L and A. So difference of this input L is multiplied, and we enter derivative GH prime. Evaluate at this, another mysterious number. This time I'm using this hat symbol, a hat. And so that's the mean value theorem. turning these differences into a nice multiplicative form, and this L and L cancels. Exact way, not L approaches 0 or anything like that. It's exact cancel. It doesn't matter what L is. Then 1 over h here, and then derivative right there. So like we did before, and we go back to this definition of GH and apply this derivative to the individual term. When we apply the derivative of the individual term, we're differentiating only on x. That's the variable, and b plus h is relatively fixed. So that derivative is the same as partial derivative with respect to x. And then we're plugging in a hat, so a hat goes there. The same thing, partial derivative with respect to x. Then plugging in that a hat is a common value. Again, this a hat and a hat having this common value right there is the magic. The little trick actually they pulled out. Very nice. Now once this a hat and a hat is a common, we can focus on the other part that's different and apply mean value theorem again by looking at this as a function only on second slot, because fourth slot is the same. So applying mean value theorem there gives us the following: 1 over h, and the difference between these two y coordinate, that's the main variable here we're focusing on, is h. So h goes out there, and differentiating this value, function fx, with respect to y slot, so y, and you put that in the y slot, another mysterious value b hat in there. So that makes, again, exactly equal, the same quantity. Again, h is factored out there, so h and h cancel. It becomes some special value of the second derivative fxy at a hat and b hat. So that was the goal. This common quantity, q, is expressed in two different values: fxy, value of fxy, and value of fyx. So here's the summary of that, what I just said. Q, the same number, is rearranged into a value of fxy, a value of fyx. So the last bit was using this continuity of this fxy and fyx. That was hypothesis. So here is what happened as we do that. This a hat and a star is some values between a and a plus l. And b hat and b star with some mysterious values in between b and b plus h. But eventually, we're going to send this l and h 0, not to arrive. The point is that order of this thing, h goes to l first and l goes to later, or they kind of go at the same time and whatever. It's all about the same quantity q. So, however we do this business of approaching 0 with L and H, Q is going to be something that we don't know actually, but if you look at the right-hand side and left-hand side, as this happened in whatever order, we know because they're in between A and A plus L, B and B plus H, as this happened in whatever order, this A hat and A star must approach A by Squid's theorem, and B star and B hat must approach by Squid's theorem B again. So by continuity, this one should approach fyx AB, because A star and B star approach AB. And that one. So from that, the first Q equals that, and left-hand side exists, gives you the existence of the limit of Q, however this L and H approaches 0. And therefore that value is equal to limit of this one as well, however this L and H approaches. So that one, by continuity, this one will be fxy, plane A and plane B. And that's the same as the limit Q. So they're all equal to each other, and that's the final bit of the proof. The continuity of these two partial derivative fyx and fxy on the entire disk, not at the AB and AB. So if you think about it, what we used here at the end is only the continuity of these two second-order partial derivative at AB, not on the disk. D. So I'm showing the statement again. They have a stronger hypothesis and a continuity on D in there, not just at one point AB, is because in this whole process we deal with fx and fy and their differentiability not only at a comma b, but somewhere around a star and a hat and b star and b hat. So the continuity of fx, the first order partial, and continuity of fy, the first order partial, is guaranteed by the differentiability of these second order and everywhere, and its continuous definitely guarantees it. So that's how this continuity is used and throughout this part. So that's the rigorous parenthesis analytic close parenthesis proof of the Clairaut's theorem, but its geometric implication of how the surface implication to the surface is quite intriguing. So that was it.